Our third common input, which we're going to consider here, is our parabolic input. And again, we're assuming this is input to our unity feedback system, which we looked at a few videos back. And so from that unity feedback system, we came up with this general equation shown here for our steady state error, so E as t goes to infinity, and we related that to the limit as s goes to 0 in our frequency domain of some function which is related to our input r of s and our open loop transfer function g of s. So in this case, because we have a parabolic input, our r of s is going to have the form of 1 over s cubed. And so again, because we have this 1 in the numerator here, this is going to be a unit parabola input. And so again, just like with our other two cases, our ramp and our step input, if we have some gain, we can just express that as a general gain k. And so I'll point out where that comes into play in our equation here in a little bit as well. So using that general equation and our new r of s, we can now say we have some steady state error for our parabola input. And so that's going to be e parabola of infinity, which is equal to the limit as s goes to 0 of s, and now our r of s is 1 over s cubed divided by 1 plus g of s. And so what we're going to see is we have the s cancel out with one of those s's, so we still have s squared, which comes down and multiplies the denominator. This term, which is going to become s squared, is just going to go to 0, so we ignore that, and we can just focus on the s squared times g of s term, so that ultimately what we get is 1 divided by our limit as s goes to 0 of s squared g of s. And so this is going to be our equation for the case of a unit parabolic input to our unity feedback system. So again, relatively specific in where we can use this. Again, keeping in mind it's a unit parabola input. If we did not have a unit parabola input, of course this would be some generic gain k, which would be represented as k here as well. So just something to keep in mind as we're applying that to different systems. All right, so let's see what conditions for g of s need to be met in order to have a 0 steady state error. So we can say we want our e of parabola as t goes to infinity to be equal to 0. So if that's true, then it turns out we must have that limit equal to infinity. So we must have the limit as s goes to 0 of our s squared g of s equal to infinity. And of course that comes from this expression here. We want to be able to say 1 over infinity, which is equal to 0. And of course it's the same basic form we've seen with our unit step and our unit ramp input, except now we have an s squared here, as opposed to our unit ramp where we just had s, and our unit step where we did not have any s. It was s to the 0, essentially. So what we can do is, again, we'll go back to that general form. So our generalized form of our g of s is shown here, where we have our zeros in the numerator, our poles in the denominator, including some n amount of poles at our origin. And so what we can say from this generalized equation is for 0 steady state error, so for e parabola at steady state, so t is going to infinity to equal to 0, then we must have n greater than or equal to 3. And so what that means is that basically we need this s squared, which is shown right here, this s squared shown right here, to be canceled out by this so that our g of s isn't going to 0. And so if we have s cubed, then it's going to cancel out that s squared and still have an s in the denominator, such that our limit as s goes to 0 of this expression up here is going to be equal to infinity. Okay, so again, remember there's a couple different ways that we can say this. We can say this is also the same as saying we have at least 3 poles of g of s at the origin. So at least 3 poles of g of s at the origin. And we can also say this is at least 3 pure integrations in g of s using our Laplace transform properties. So at least 3 pure integrations in our open loop transfer function g of s. And so again, recall that all 3 of these are just saying the same thing in a different way. So just like we looked at with our previous systems, let's consider what happens as we let that n value, the exponent up here for our s, becomes smaller. So first of all, let's consider if we just drop right below that and say what happens if our n is equal to 2. So if our n is equal to 2, we have the limit as s goes to 0 of s squared g of s. And so if we have s squared and then this term is going to be s squared as well, of course the s squareds will cancel out and we'll just be left with the limit of everything else going to 0. And so as you can see, the s's are going to go away, they're going to be going to 0, and so ultimately we'll just have z1, z2, so on and so forth in the numerator. So we'll have the product of our zeros divided by the product of our poles, p1, p2, and so on. And so ultimately what that gives us then is some finite steady state error. So finite steady state error. So that's for n equals to 2. So what if we continue to drop that? So if we have for n equals to 1, and so actually we're going to see this is true for n less than or equal to 1, then we still have this limit of s goes to 0 of s squared g of s. And so let's consider sort of explicitly the case of 1 first. So in this exponent, let's say we have 1, so of course that's just s. So our s is going to cancel out with one of these, but we're still going to be left with this s here. So then the limit as s goes to 0 is just going to be equal to 0. So it doesn't matter what our g of s is because it's multiplied by s. Similar thing if we let n equal to 0. So in this case, if our n is equal to 0, we now have no s's in the denominator here, which means there's nothing to cancel out these s squared. And so we have the limit as s goes to 0 of something times s squared. So of course that's still just going to be 0. And so whether we have n equals 1 or n equals 0, then we can see that we're going to have infinite steady state error. And so over the course of these 3 videos then, hopefully what you're seeing is that of course our steady state error is very dependent on what type of input we have to the system. Another thing to keep in mind as well that I've tried to point out in each video is that for all of these we've considered unit inputs. So unit step, unit ramp, unit parabola input. And so that's what these circled equations are for in each video. If you want to adjust that, then you just have to update the numerator here to reflect any gain in the input signal.